All right, so we're going to be looking at two different methods this week. One is called the full orthogonalization method, and one is called GRMES, generalized residual minimization error. Okay, so that's what we're going to be looking at. I'm going to sort of give a general overview right now. It's going to be similar to other general overviews that I've given, but with a more directed eye toward exactly what we're going to be doing this week. Okay, so again, we're solving the system AX is equal to B, and we have some initial guess X naught, and as usual, we define the residual R naught to be equal to B minus AX naught. So R naught is going to be equal to B minus AX naught. Like this. Okay, and so we want to, our goal is to find some delta that lies in some smaller space than Rn, and we're going to form X. Excuse me. We're going to form X. X naught is equal to X plus delta. Delta is called the corrector here. Ideally, delta is going to be the exact difference between X star, the exact solution, and X naught. But obviously, if we could do that, then we would just, if there's a reliable and fast way to do that, we would just do that and solve the problem exactly. So the idea then is that delta is going to be an approximation. Delta can only be an approximation. Typically, the only thing that we can expect out of delta is that it's going to be an approximation. And so what we want to do is find a low dimension subspace for delta to live in. Okay, so again, if we could find an exact subspace, it'd just be a one-dimensional subspace that delta lived in, that would be great. But the idea is to sort of create a sequence of subspaces such that each time we add to that subspace and get a bigger subspace, we sort of are picking up bigger and bigger parts of delta, right? Because delta is a vector in Rn. It could have a component that lies in any given subspace, and so the idea is we want to grow our subspaces so that each one of those subspaces contains a bigger and bigger part of delta. That's one way to think about this. And so we're not just going to be taking like random subspaces that happen to be a smaller difference, a smaller dimension than the dimension of A, which is in. We're going to sort of, we want to, what's the word I'm looking for? Intentionally grow our subspaces toward a subspace that is going to be more likely to contain delta, or at least more likely to contain big components of delta. And so one way to think about what we're going to do then is, let me get a different color chalk here, is we're sort of going to restrict our universe to this smaller subspace. We're going to restrict our universe to this smaller subspace. Now, what exactly that means, there's various ways to interpret what it means to restrict our universe to this smaller subspace, and depending on exactly what that interpretation is going to make the algorithms, like the actual algorithms, a little bit different. So it's going to give rise to different algorithms depending on exactly what we mean by restricting our attention to this universe. But in either case, we want to have delta, as I said over there, to be in whatever subspace we're thinking about, K. And we also want to have the residual, or the residual of the new vector. So we want B minus A times the updated vector to be orthogonal to some subspace L. And again, what L is going to depend on what our interpretation is of this of this notion here of restricting our attention to a smaller subspace. Okay, so then let me just point out that b minus ax naught is also equal to r naught minus a delta. This is a standard computation that we've done several times, and we want r minus a delta to be orthogonal to L. Okay, and if you need a reminder of this computation, b minus ax is equal to b minus a. Well, x is going to be equal to x naught plus delta. So this is x naught plus delta, and then we're going to have b minus ax naught minus a delta. Okay, and now b minus ax naught, that's exactly what r naught is defined as. Okay, so now the question that we have to ask is, what are the subspaces that we're going to use? I mean, if we can't find a sequence of subspaces that kind of does the thing that we need it to do, if we can't find a sequence of subspaces that does the thing that we need it to do, that is, becomes a better and better approximation to a space that delta might live in, then this method doesn't really work. And so the subspaces that we are going to use will be called the Krylov spaces, denoted this way. K sub m is going to be an m-dimensional subspace. We put here A for our matrix and R naught for our vector. And there's various ways that we can denote this. If the matrix is kind of fixed and we want to emphasize the starting point, we can just call it a km of R naught. Or if we just want to be even briefer, if the starting point, the starting residual vector is known, we can just call it km. And it's going to be the linear span of the following set. So K sub m is going to be equal to the span of the vectors r naught, ar naught, all the way up to a to the power of m minus 1 r naught. And as we will see, if we use this as our sequence of spaces, we're going to get something that as it enlarges, as m gets bigger and bigger and bigger, is going to contain a larger and larger piece of delta that is the error between our approximate delta and the actual delta is going to get smaller and smaller and smaller. That is sort of the interpretation. Now, again, when we talk about the error getting smaller, there's various ways that we can measure that. That is related to the question earlier when I said we're going to restrict our universe to a certain subspace. These are all related, and there's different legitimate interpretations of what that means. And each one of these interpretations is going to give a slightly different system. We're first going to learn about the full orthogonalization method, not in this video, but in an upcoming video. That's what we're going to learn about first, and then we're going to learn about the GRMES method as well. So, and we're going to program them and implement them. So it's all something that we can program. But before I can get to those methods, I'm going to make a video where I just remind you about some basic ideas about projections of vectors onto subspaces and things like that, because those formulas and those ideas are going to be necessary to understand them.